Okay, so we're going to finish up this discussion of testing. So testing.r, we'll wrap that up today. And then we will meet some example data that you're going to work with in the homework, the yeast data. I'll show you those today. And we'll start doing some data analysis with bioinformatics data. So we have an M by N matrix of numbers. We'll look at the yeast data, and let's start exploring. What kind of pictures can we make? What kinds of data basic sanity checks can we do? Some multivariate techniques that help us to understand what's in the data, because we have lots of data. We have thousands of rows and some number of columns, and it is hard to look at a giant matrix of numbers. What pictures do you make to see them? It turns out there are some techniques from multivariate statistics that are pretty handy, like principal component analysis, something that's related to that called singular value decomposition, cluster analysis. These are all handy, and we'll see them in action with the yeast data. I'll show you what they can do for you. So in the testing.r script, we have worked through much of this, and we've kind of focused on this idea of the false discovery rate. So if we have thousands of features and we do a hypothesis test each time, getting a p-value each time, we have to be careful about what we can say statistically about the resulting list of things that we pull out. Here's my 30,000 genes that we started with. Here's 200 that I think are interesting. And we have to be careful about what we say. How confident are you in the claim that these are interesting? False discovery rate is a good way to balance between getting lots or a sufficient number of interesting things to look at further, while balancing with error probabilities. Arguably more suitable to this setting than type 1 error rates and plain p-values. Remember that you can get false discovery rate estimates, basically what we called Q-values, using that p.adjust function in R. It's a built-in function, and it will do a variety of p-value adjustments for multiple testing. If you want an FDR, you just do p.adjust. Here's my p-values, comma, method equals FDR. And it basically reproduces what we did manually and what we saw in that paper, the Story 2003 paper. Okay, and then what I wanted to do to finish discussion here was comment on correlation. A couple of different ways that there can be correlation that we talked about already. One being the difference between a biological and a technical replicate. I referred you to this paper, but I haven't posted that paper. So let me post that today. This is a paper from Gary Churchill. He's a biostatistician, and he works at the Jackson Laboratories, where they manufacture mice and stuff like that, genetically bred mice. And he was kind of deeply involved in the early days of microarray stuff. How should you design an experiment? How should you do basic stuff with these types of data? So I need to look that up. I'm not going to be able to find it on Google right now, but I'll get a paper posted. I'm not going to say a whole lot more here than I've already said. Just to reiterate, there is a difference. It matters how you obtained the sample that you built a column in your data set on. So if I have a column representing a single assay, like a microarray chip or a NGS run or whatever it is, if that didn't represent a draw from the population of interest, but rather was just a rerun of a sample that was taken from the population, then we would call that a technical replication, not a biological replication. And I'm going to show you a simulation down here that kind of illustrates what can go wrong if you have correlation. The common thread, whether we're talking about biological versus technical replicates or repeated measures on the same individual, like if we have time course data come in once a month and I'll do a microarray or a sequencing sample of your toenail clippings or something, and we'll track some medical outcome over time. So I have multiple measurements on the same person. And I'm specifically probably interested in like modeling how things change over time. You're exposed to some poison, and let's watch as the stuff that we take out of your toenails, spikes in the concentration of poison, and then it tails off as the poison is processed and removed from your body. So we might specifically design an experiment so that we can look at and model time course type things. And then the other consideration that again has to do with correlation is what if the features themselves are correlated with each other? We have thousands of genes maybe, and if we're going to do this, let's go gene by gene and compute a t-test, get p-values, and turn those p-values into a false discovery rate, say. One of the assumptions behind doing that whole process of let's look at the histogram of the p-values and use that picture to decide what proportion of the features are null and get an actual FDR estimate is dependent on those p-values being statistically independent from one another. And they would not be statistically independent from one another if the genes themselves were correlated. Like suppose these 50 genes operate together in some pathway. And here's another set of 25 genes that operate in a different pathway, and so on. So when one of them in that pathway turns on or lights up or turns up, the others respond similarly. They're correlated. Okay, so let's do one or both of these simulations just to see why should we even care? Why does it matter whether there's correlation in the data? Let's come down here. So I'm going to do a simple little simulation with what parameters? Okay, we're going to set sample size n to be 100, and we are going to create what is M? 1,000, I think, features. So yeah, let's do M is 1,000. And then we will do N, the sample size is 100. Let's randomly generate some means for the features. So mu1 will be the mean number, the expression level, the intensity for the M genes in comparison group 1. And mu2 will be the corresponding number in comparison group 2. So we're pretending that we have two comparison groups. I'm just randomly generating these uniformly between 8 and 15. Totally made that up. And I'm making the means be the same. So every gene will have, at this point, once we've done this, every gene will have the same mean. There's no differential expression in these data yet. We're going to cook in some correlation, and the way we're going to do it is have 200 groups of 5 correlated genes each. We have 1,000 genes, 1,000 features. We're going to say the first 5 they act together somehow. They're in a pathway or in some kind of common mechanism. So they are correlated with each other. The next 5 are correlated with each other, and the next 5 are correlated with each other. The genes that are in the first little cluster are independent of the genes that are in the second little cluster, and so on. So the only place that there is correlation is within these little clusters of 5. If you think about, if you're familiar with what a covariance matrix is, the covariance matrix for my data would be an M by M matrix. On the diagonal would be all the variances for the features. Here's the variance for gene 1 in first row, first column. Here's the variance for gene 2, second row, second column, and so on down the diagonal. And then all the off-diagonal stuff would be covariances. Here's the covariance between gene 1 and gene 3. And there's the covariance between gene 100 and gene 242. You can turn covariances into correlations by just rescaling them. So this is like a scaled correlation matrix. And what we could say is that it has a specific structure. It looks like this. Let's call it sigma 0, dot, 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 sigma 0, where sigma 0 is a 5 by 5 matrix. And in all these little off-diagonal chunks, there's a 5 by 5 matrix of zeros. So dot, 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 and dot, dot, dot. And this is symmetric with respect to the diagonal. So you could call this a block diagonal setup. They are not independent. All the features are not independent because within that little clump of those first 5, there's non-zero correlations between them. They're not correlated with anybody else, but they are correlated within their little clumps. So there's little clumps of correlated features. That's what we're going to set things up for, and we're going to consider what happens. So I need to library this in. This allows me to generate multivariate normal data, which is kind of where we're headed here. If we're saying there's correlated observations, I don't want to just generate a column from the normal distribution and another column from the normal distribution. There's correlation, so I need to generate things kind of jointly. That's why I need a multivariate normal. You don't have to be able to reproduce this code. Just follow along. What we're doing is what I described in words. Setting up omics data where there is some correlation in little pockets. I am going to make it so that the first 300 features are differentially expressed like we did previously with this little simulation. So there's a mixture of differentially expressed features and non-differentially expressed features. Let's see what happens. So first we're going to simulate the data. And now we're going to go through and compute p-values. So suppose these were our data. Here's your Excel spreadsheet from your collaborator. There's 1,000 features, and in this case there's 200 samples, 100 samples per comparison group, treatment and control, say. And common task would be find the subset of those 1,000 features that are statistically significantly different between the comparison groups. So let's do a t-test like we've done before. Here's just a 2-sample t-test, gene by gene, and we pull out the p-values. Here is a histogram. Did I already run that? No, I did not run that. So let's run that and then make a histogram of the p-values. Looks like that, which looks like what we're used to expecting. Peak at the left over near 0, representing the interesting features. Flat representing all the null features, which will usually be the largest proportion. Most of the things are not going to be different, depending on what you're studying. So no indication of any issues here. What might I check? For me to do statistical inference. Statistical inference is p-values and confidence intervals. That's making decisions and claims and assigning a specific level of confidence to those decisions and claims. 95% confident of such and such. For you to be able to say that, you have to be able to count on some long-range behavior of the methods you're using. 95% confidence interval, for example, I say I'm 95% confident that the true pH of this lake is between 5.8 and 6.9. For that to be a valid statement, I would need to be able to say, if you were to repeat this process many times, go take samples from the lake and compute the averages, compute the standard deviations, put them together into this formula, which is a 95% confidence interval, 95% of the times that you repeated that whole thing, you would have captured the true pH, mean pH of the lake. And if you do a hypothesis test, I've selected my features based on whether they had p-values less than 0.05, and that allows me to say something about type 1 error rates. So let's check something. The null features in this example are the last 700. We have 1,000 features total. The first 300 are the ones that we made differentially expressed. Last 700 are not. What proportion of that last 700 would you expect to have p-values less than 0.05? We've answered this one before. Last 700 are null features. They are not differentially expressed. What's the distribution of a p-value if the null hypothesis is true? If you were to draw the picture in the, let's say, the whiteboard, histogram of p-values when the null hypothesis is true, p-values, distribution, height, is this flat thing that we talked about. Probability of seeing a p-value less than, insert your favorite threshold, call it C, like 0.05, would be the area under this thing to the left of C. So the probability of getting a p-value less than 0.05 when the null is really true, a spurious finding, is 0.05. So what proportion, if I take out, here's the last 700 features. And if I were to table up the number of them that are less than 0.05, if the assumptions of my methods hold, then this should be about 5%. We have 33 out of 700, about 5%. So we have some correlation in the data. We did statistics as if there weren't any correlation. We just did t-tests and everything. And it doesn't look like we have much of a problem. The type 1 error rate, the error rates that we would be appealing to when we back up our findings, haven't been grossly affected. We could probably make it a problem if we raised, say, the correlation. Let's make the correlation really high, 0.99, because it was just 0.5. That's not very high correlation. But now there's this correlation within chunks, and it's very high, very tight correlation. What happens now? Let's do the same thing we did above. Table p-vals 301 to m less than 0.05. .43, a little bit higher, but again, not that bad, actually. So the short story is correlation can make a difference. It can hijack your ability to do valid statistical inference. If we spent enough time here and tweaked this, increasing correlation, increasing maybe the size of the clusters where there is correlation, I guarantee I could make it so that like this error rate, I expect this to be about 5%, guarantee I could make this be higher than 5%. Which would mean, like hypothetically in the real world, here's your data set full of omics data. You go do p-values and false discovery rates, you come back and say, here's my list of 43 or 100 whatever interesting features, and my estimated false discovery rate is 0.05. You could be incorrect in that claim. It could be not 0.05, but 0.1 or something like that. If there's correlation, and if there's sufficiently strong correlation and you don't account for it. Yes?
So this could be because the materials that you're scanning are related.
Correlation can happen if in a variety of ways. The genes, the features themselves could actually like biologically be correlated. When this protein is present, these other proteins are present because they operate in the same pathway. They show up together, they go away together. That would be correlation. Multiple measurements on the same mouse or wheat sample or something like that would be a source of correlation because it's multiple measurements on the same individual. It inflates the error rates, yes. Multicollinearity is a little bit different. It's different. That talks about redundant information in a collection of variables, like you want to predict lifespan for US adults or something, how long you're going to live, and you have covariates, which include age, gender, and all that, and you have median annual, or you have annual income in dollars, and you have annual income in pound sterling or something. Those two variables are perfectly correlated. There will be multicollinearity because there's redundant information in there. And in particular, if you put both of them in a model, you can't tell me if you hold income in dollars constant, what's the effect of changing income in pound sterling? You can't separate those out. So you can have problems trying to fit that model. Multicollinearity, think in terms of like covariates, where some of them are giving you redundant information. If I know income in dollars, I don't need income in pound sterling. I could just convert it. Does that make sense? So we're not exactly talking about that here, although they would share some characteristics. You could have columns in your data set representing different wheat samples or something, and if they are highly correlated, like technical replicates of each other maybe, if they are highly correlated, you have some similar implications as that multicollinearity thing. Either scenario is bad news for you as the statistical analyst. Multicollinearity messes up your ability to fit a model. So you would want to, think about, might that be in my data? And if it might be, I'm going to remove from consideration variables that are redundant. I don't need them, so why put them in there? If you have correlated data, the wrong answer is to just ignore it and say, I don't want to worry about it. Because you can have issues like I was referring to. Here's my 100 and something interesting features. FDR is 0.05, when in reality the FDR is 0.1 or 0.15. So you don't want to give biased, results. Okay, so conclusion, comments on this issue of correlation. Correlation is an important issue. It shows up a lot in practice, I think. It does complicate the analysis options you have. Every study that results in data that you are looking at, I would make sure that you ask questions about it. is there correlation in these data? How might there be correlation in these data? What questions should I ask of my collaborator to make sure that I know if there is correlation in the data? Once you know that there is correlation, you have some options available to you. There are methods for dealing with correlated data, like even in the omics case. Suppose we had time course data for each of several individuals. We have assays at multiple time points. 1 month post-surgery, 2 months, 3, 4, 5. Then suppose we go to one gene and we have these 5 measurements for individual 1. And then we have 5 measurements for individual 2. And so on. We have like profiles for individuals. Correlated data, because I have multiple measurements on the same individual. It's not necessarily a bad thing as long as I deal with it. So what I might do to take advantage of this type of data, which is actually rich, it allows you to talk about changes over time, which is a pretty neat, question to ask scientifically. So we could do things like, let's estimate the population average time course over time for the treatment group and compare that to the population average time course for the control group. So you can actually fit curves gene by gene and do a test. Put a p-value on, is there a difference in time course, like these functions, for gene X? So correlation is important. Always wonder, where is it if it is here? When it is there, think about what you can do to accommodate it, deal with it. One story that we're seeing back from this simulation is that some correlation does not necessarily have to be accounted for. If you feel like there may be correlation but it's minor, like relatively low, then chances are it's really not going to have a big impact at the end of the day. So think of it as something that can have a big impact, and just be aware of it. So questions about correlation and how it can come into play. So question about if you have data, how can you go about investigating, is there correlation? And if there is correlation, like what's the pattern? What kind of correlation? I think the easiest first step is just to think about or to have an in-depth conversation with the collaborator. Tell me about how these data were collected. Tell me about the data. Well, we got mice and we did this and we grew them and we did that and we got 30 numbers here. Okay, so those were 30 different mice? No, every mice was run in triplicate. Okay, we just figured that out. So I think step one is just conversation with the collaborator to really understand what happened to result in the data. There are things you can do to investigate whether there is correlation, like these 5 samples were run in a batch last week. That's the only time we had to do it. We can't run all 30 samples on the same day because it takes too long to go through the instrument, for example. So we have to break them into batches. Here's batch 1, which was 5 samples. There's batch 2, which was 5 more samples, and so on. You could compute sample correlations. Let's look at correlations within those 5 in batch 1 and in batch 2, and you could just look. Do they look like substantial correlations? So yeah, I guess that's my answer. Think about the design of the study and then do some simple like summary statistic calculations. What's the sample correlation between batch 1 and batch 2 or within batch 1? And just kind of qualitatively get a feel for whether it's substantial and should you even think about it further. So there are techniques like we talked last semester about generalized estimating equations, which is a regression technique that allows for or accommodates correlated data. And the nice thing about it is that you could be wrong about what the correlated data looks like what's the actual name or structure of it, and GEE will still give you robust estimates. So there are techniques that are appropriate for correlated data. Okay, so I did want to go through this briefly. I think I asked you on your homework to do a Bootstrap analysis. This whole script is about testing. There's different aspects to an analysis that we'll meet along the way. Some of what's coming is more exploratory in nature, like principal components and cluster analysis and stuff. That's making pictures and getting qualitative understanding of a data set. Testing is inference, statistical inference. I want a confidence interval or I want a hypothesis test to make formal claims, formal decisions. In the context of testing, it can be useful to know about something called the bootstrap. So up above, when we've simulated data, we did t-tests. We just did 2 sample t-tests comparing treatment to control. Think about other things that you could do to put a p-value on each of the features, each of the genes. You could do ANOVA. If you had more than 2 comparison groups, you don't do a 2 sample t-test, but you could do an ANOVA. I have 3 fertilizers that I'm considering, A, B, C. Let's go to gene X and compute a p-value. Is the mean different between the 3 fertilizers? You could do that. You could do a regression model. If you wanted to model intensity as a function of treatment group and age and gender and any other covariates I have for the columns, you could do a regression model and get a p-value. Okay, if you do a t-test, let's think about that. And let's say we just have 2 comparison groups, treatment and control. Let's say it's a small sample size, which it often is with these types of data because it's expensive, often, to create this type of sample. Give me a tissue sample, and I'm going to run it through this instrument that I have to pay hundreds of dollars to rent for the day, from the facility on campus. There's reagents and laboratory materials that have to be paid for. There's the assay itself that had to be bought from the company that costs hundreds of dollars. So it may be that we have high-dimensional data, 30,000 features, but we only have 10 observations, 5 treatment, 5 control. What do you know about a t-test? Let's say pick one of the genes. We have 10 numbers for that gene. I have 5 for treatment, 5 for control. And I want to do a test. Is the mean, population mean, the same for treatment and control for this gene? What assumption are you aware of that I need to make if I'm going to go do t.test and pull out the p-value? What assumptions are you aware of that the t-test requires? Population distribution type assumptions. What does the t-test assume about the data or the distribution of your data? It does assume normality. If you have a large sample size, it doesn't matter because there are limiting results that say t-test is fine, if n is bigger than 30 or something, even if the population is not normal. But with a small sample size, like 10, 5 in each group, you do have to worry about whether it's normal because the p-value you're going to get out won't necessarily be right if the population was not normal. Okay. So you have 30,000 features on your assay. Are you going to go through all 30,000 and try to assess, are they normally distributed or not? And even if you do that, if you only have 10 numbers, like here's 10 normally distributed numbers, so let's do 5 for one of the groups. So X is R norm 5. Give me 5 numbers. There's my numbers. Are they normally distributed or not? What techniques are you aware of that I could use to assess that? Tell me a plot I could make to try to guess whether these came from a normal distribution. What picture might you make if you wanted to know whether some data looked normal or not? Yeah, you make a histogram. So let's make a histogram of our 5 numbers. It's like that. I only have 5 numbers, so this is going to necessarily be real choppy, you know. Hard to see much like about a whole shape of a distribution based on 5 numbers. There's also something called a QQ plot, so QQ norm X. And what I'm asking is, does that roughly follow a straight line? Here again, I only have 5 numbers. So, you know, if one of them happened to be off, it would look horrible. In this case, it doesn't look that bad, but if you were to just play around, like generate some normal data, 5 observations, and do this, you can get some weird looking pictures. Like here's one. That doesn't look straight. That looks kind of curvy. My point is, with a small sample size, it's not easy to assess whether normality holds or not. So that's why it's nice to have options which are called non-parametric, in the sense that I don't have to say normal distribution. I can parameterize the population distribution. It's the normal with these 2 parameters, mean and variance. Non-parametric would be an alternative that does not require that we specify that. Okay, so one common non-parametric approach that is pretty generic and is a good tool to have in your toolkit as an analyst is called the Bootstrap. And all the Bootstrap does is approximate sampling distributions. Approximate a sampling distribution. When we do inference, p-values, confidence intervals, it's driven by sampling distribution. Sampling distribution is just a distribution, but it's specifically a distribution of a statistic, like a sample mean or a t-statistic. We need to know about that before we can do inference, confidence intervals, and hypothesis tests. The Bootstrap is a resampling technique where you sample with replacement from your observed data, and each time that you have done that, like in our case, I'll show you down here. We sample with replacement, we recompute the statistic of interest, and then we compare the original statistic to the simulated, like resampled versions. So let's see an example. We are going to do 4 things. We are going to come and replace those t-tests that we did. Instead of relying on the normality assumption, which may well not be true. I don't know. It's hard to assess for thousands of things at once. Let's change our procedure to get the t-test for, let's say, feature I. So I'm going to loop through all the features, all the genes, I and 1 to M. And for the ith gene, let's go ahead and write down the t-statistic. The t-statistic is a sensible 1-number summary for differences between the comparison groups. It's a scaled mean difference. So are the groups different? This is a natural number to look at. I don't mind this number. I don't trust, though, the p-value. So I'm going to replace the way I get the p-value. Okay, so here's what I need to do. I'm going to have a new loop down here. Right now, I'm looping over the features, like gene 1. For gene 1, let's start doing some stuff. First, let's compute the 2-sample t-statistic. Hang on to that. I want to put a p-value on that. How unusual is that? Without having to assume normality. And in order to do it, I'm going to kind of simulate multiple versions of our data. So I have a loop over capital B Bootstrap iterations. Capital B for now is 100. That's what I defined it to be up at the top. So for each of 100 times, we're going to generate a kind of pseudo sample based on the one that we saw for gene I. So for gene I, let's come into this loop, Bootstrap loop, and let's do the average of my observed data for gene I plus a random sample with replacement from deviations from that average. So I have the t-statistic for gene I. I also have this thing I'm calling residuals for gene I, which are deviations from the group-specific means. So y, the first n observations, is group 1. Subtract off the average for group 1. For the remaining columns, the treatment groups say, subtract off their mean, their average. So these are now, if you just look within the first comparison group, all of these columns have average 0. All of these columns have average 0. These represent deviations from the overall average. What I want to do in the Bootstrap is generate a kind of a new version of our original data in such a way that we force the null hypothesis to be true. The p-value, we've talked about this, is the probability if the null hypothesis is true, you'd see a statistic like yours or something even more extreme. We talked about that with the alignment assessment, like how confident am I in an alignment. We got our alignment score, and then we got a bunch of simulated versions of the alignment score when we forced the null hypothesis to be true. And then the p-value was just the proportion of those simulated scores that were as big or bigger than our original one. We're doing something very similar here. We are sampling with replacement from residuals and adding those back to the overall mean. When we did that, we killed any difference, systematic difference between the groups, because these things have mean 0. These are just like deviations from means within each group. So when I sample with replacement from them and add them to the overall mean, I have, again, some observations in the control group and some observations in the treatment group, but now the mean difference between them is 0. I've forced it to be 0. I've forced the null hypothesis to be true. Now I recompute the statistic of interest using these simulated or bootstrapped data, and I record that. So for gene I, I'm going to go for capital B bootstrap iterations and get simulated bootstrap versions of my statistic under the null hypothesis. And then the p-value is just a proportion. What proportion of the simulated null version of our test statistics were as big or bigger than the original one that we saw? In absolute value, because I'm basically wanting a two-sided p-value, a two-sided alternative p-value. So hopefully some of that will stick for you. I'll revisit the Bootstrap a couple of times throughout the semester because I think it's a really useful and general technique. It's not limited to t-tests. It could be done to regression. It could be done to survival analysis. It could be done to pretty much anything you can do statistics on. If you're concerned about the sample size is too small to worry about specific distributional requirements, the Bootstrap might be a good solution. So here we're going to do the Bootstrap, looping I equal 1 to 1,000, and inside each time, looping again, I equal 1 to 100. So this might, if you have a real world size data set with tens of thousands or hundreds of thousands of rows, that's a practical limitation. It might take a while to actually run. But let's run this real quick. While that's running, I think I posted an announcement on eCampus, but I don't think I announced in class. I'll be at a conference on Friday of this week. So instead of a live lecture, I'm going to post a recording of a previously recorded lecture. So don't come here on Friday. I will see you back here on Monday. But do watch the lecture video. So now I have p-values. Boot p-vals, 1,000 numbers, and these are just proportions. Here's the first 10 of them. Bunch of zeros. Okay, let's look at another subset of 10. The first 300 were differentially expressed features. We simulated the data so that the first 300 actually had mean differences. So I would expect to get small p-values. I would expect to tend to get small p-values for them. It turned out that I got very small p-values for them. That means none of the simulated Bootstrap test statistics were as big or bigger than the ones we originally saw. When you get out towards the latter collection of features, though, these are null features. These are features that are not differentially expressed. So you do see larger p-values. The nice thing about the Bootstrap is that these p-values are correct. We talked about, what if you have correlation and you do a two-sample t-test? The type 1 error rate, these error rates might not be what you claim they are. I have an FDR 0.05. No, you actually have an FDR 0.15 because of correlation. The Bootstrap can be counted on to maintain the proper interpretability. So if you do a Bootstrap and you get p-values like this, you can say estimated FDR 0.1 or something. You could take these p-values and get FDR, even if the distributions are not normal. So you got around the assumption of normality for a t-test. Other times where like a Bootstrap is handy is when you maybe don't have a formula for how to compute a p-value. Like a specialized a type of analysis where you have something specific that's very specific to your setting that you want to compute. Like what's the fraction of the contaminant out of this list of 30 common contaminants and the things that my company makes, what's the proportion of them made up by this subset of 3 or something? And I want to make a decision, is that proportion greater than 0.2? Something kind of specific that doesn't necessarily have like a formula, that's a t-test or that's an f-test. You can often translate that to a Bootstrap scenario. So if there's some statistic that you can compute that makes sense, like a t-statistic made sense here, and all you need to do is get a p-value for that statistic, you can do that with the Bootstrap very easily. All you have to do is simulate by resampling with replacement and recompute your statistic. And then a p-value is just the proportion of them that are as or more extreme. You can also use the Bootstrap to get confidence intervals. We don't have time right now to talk about it, but think of the Bootstrap as a non-parametric way to estimate sampling distributions. So hopefully some of that can be helpful. Next time we will start with exploratory data analysis, so cluster analysis, exploring how the samples grouped together are some of the, like we'll see with these yeast data, we'll see there's 2 technicians who ran these samples. And if you do cluster analysis, you can see that there's 2 technicians that ran the samples. Here's the arrays done by technician 1, grouped together, clustered together visually. We will see it in a picture. And here's the arrays for technician 2, grouped together, clustered together. So you make a picture and you just learn something kind of big or thematic about your big data set. Technician effect. I can see it, just in a picture. We'll also talk about principal component analysis and singular value decomposition, which do similar things in different ways. But you take a big data set and you boil it down to simple stories that you can hopefully interpret and learn something about the data with. Okay, so I will see you Monday. I'll post on eCampus when the video's been posted so that you can watch it, but see you Monday.